Good wishes, Physics 103 class. This is lecture 4A, and our next topic is multiple expansion of potential. Now, slowly, we'll be exploring things which are a little new to you. So far, we have been talking about things that you know, but we are dealing at them at a deeper level. But now on, we'll do things which are actually new to you, at least to most of you. Okay, so let's start multiple expansion. Uh, what is the motivation? Motivation is somehow getting to know localized charge distributions that are localized, whether it's in a star or inside a solid in an atom. And such that we can have a better view from a very bird's eye view, from a very far point. Okay, that's most of the. I'm not interested in minute details of how the charge distribution is there, but I would like to have the fair amount of knowledge of, especially the way it affects me, the way it is useful. All right, not every detail about the distribution. Okay, for example, in the class, I don't if your marks, okay, I do if you give me 638 people's marks, I won't be able to say much. But if you give me the average, okay, the mean, the median, the variance, okay, I know the distribution better. In that sense, we get to know in the first moment, these are actually various moments of any distribution. So that is the idea. Can I get to know the localized charge distributions better, okay, from a far point, and make a hierarchy of things, okay? I think I'll keep harping on this point as we go along. So let's have a localized distribution Q here, let me say, okay. But this localized distribution can contain surface charge, uh, plus minus charges, line charges, surface charges of various shapes, volume charges of all kinds, both positive and negative. Okay, and let's set up my coordinate. Let's say this is my origin. This is the charge distribution, and here I set up my origin here. I could have chosen it according to convenience. This origin also, for example, could have been inside. Okay, and then I've shown it deliberately at a very far point. Okay, and so here I want to know the describe this charge distribution, okay, at this point. Okay, so this is the r vector from my origin to the field point. I'll keep referring to this point where I'm viewing it from, which is very far from the charge distribution, and that is the field point. Okay, and these r primes are from the origin, the source points. Okay, and the effect on where I am, okay, is that is our Griffith's curly r. Okay, where, for example, if I am looking at the effect of this charge on this point, this curly r, we are already familiar with these notations. And so this is r prime to any of that. So I'll be able to describe from my origin the r prime, the prime coordinate, the source. All right, then so this set up my, so what is my m? Of course, I am viewing it from very far. Okay, so we have seen that many distributions sort of reduce to a point charge from a distance. Okay, from a very far off. So that we have already seen it many. Okay, so for example, let's say if net charge is zero here, does it mean they have no effect on this? So how does the charge distribution affect the field at a distance? Okay, in fact, it's an urgent question because most of the bodies that I deal with, okay, whether it's in astronomy or even or in daily life, are neutral. Their net charge is zero. That doesn't mean that the charges they consist of has no effect on me, where I'm viewing. So that's the basic motivation. All right. So how do I want to do that? That I now in electrostatics, it's clear that if I know the potential at that point because of this charge distribution, okay, then I can get to know everything about its effect on the field point, okay. And hence this VR, if I get to know in various forms, I'll be able to use it for my purpose according to my requirement. All right. So let's see. So the objective is, can I expand VR in powers of 1 by R? R is the distance from the origin to the field point. All right. So we sort of know how to expand a function, for example, in Taylor series. Okay. So this is a Taylor series. This is f double prime of 0. We are also familiar with the idea of various moments of a distribution. For example, if there is in mechanics, you would have done the total mass. Total mass tells you something about the mass distribution, but very little about how it is distributed. It's only total mass. Then you calculate where is the center of gravity. There is a sort of first moment. Okay, we say that the center of gravity will calculate because the way the mass is distributed around, and it's the first power of the position. Okay, but then with the second power of the position, we get to moment of inertia. So this is what we are already familiar with. Okay, for any distribution we would like to do is actually called the higher and higher, more and better. I get to know the distribution better and better as I keep on getting to know the higher and higher moment orders of the momenta. Okay, the average, the first momenta, the second momenta, third momenta, and so on and so forth. Okay, so in probability statistics also you would be studying this in much greater detail. Okay, so I have already introduced you. For example, I have shifted my origin inside to match with the book. Okay, so R prime, and this is the field point, and so this is the R, and this is my curly R. And any particular distribution d tau prime. These are prime coordinates in the source, and alpha. I want you to remember that the angle between the source coordinate and the field coordinate is the angle alpha. All right. So our aim is to expand the potential VR here, okay, as sum of series of momenta. So what I'm saying is we are familiar with series expansion in maths, okay, Maclaurin expansion, Taylor expansion, but this is three-dimensional R, okay, and we know the idea of momenta. So our aim here is to expand the potential at a very far point as a sum of series of momenta. Okay, so let's say we call that the multiple expansion of potential. Of course, it's at a far point. Okay, so we know VR for any generalized distribution. I'm taking a row, prime coordinate R, curly R here. In fact, I should have the figure right here. Okay, so 1 by 4 pi epsilon naught dq by R. That's my R at my position here. Now I want to expand this in what I call the various momenta, and that I call the multipole expansion. So first thing I note is that this R square, R here from here to here, R square, I can express in terms of R squared, the cos R prime square, okay, minus 2R R prime and cos alpha. This we have done often enough. All right. Now I take the advantage of the fact that I'm at a far point. So this multiple expansion is possible because of this crucial assumption that I am looking at it from the very far point. That is, I want to make something small and then expand. That's what we do in most expansions, right? So what do I then do? I take out R square common, okay, such that the first term is 1, second term is R prime by R whole square, and this is minus 2R prime by R. Okay, so you can see my intention. My intention is that R prime is a localized distribution, so it is here, okay, whereas R is very far away. So can I express this R this 1 by r, or this r, in terms of a small quantity that is r prime by r. That's the intention. All right. So that is very well possible. Okay. So I can express this r in terms of r root over 1 by epsilon, where I write it down as epsilon is r prime by r prime by r minus 2 cos alpha. Okay. So this is the definition by epsilon. All right. So this will be crucial. Um, so this epsilon is of course small and much, much less than 1. All right. So let me put this epsilon into. So if I look at 1 by r, because what I'm interested in is 1 by r here. So 1 by r is 1 by r. That's the main distance that I'm interested in, of my interest. And I then expand it in terms of 1 plus epsilon is a small quantity minus half. And this expansion we know how to do. All right, so let's do that. So 1 by r, so I just expand minus half, of course, alternate minus plus 3 by 8 epsilon square. This is my epsilon. Okay, epsilon square, and 5 by 16 epsilon cube, and so on and so forth. Now what I'll do is I'll plug this epsilon into this expression after having expanded it. All right, so that's what I do. So that is 1 by r, my first term. My second term I write down. Okay, uh, that is straightforward, this term alone. Okay, in the second term there is a square term of this. Okay, so that is, so that becomes square, and there is a square here. Okay, and then the minus 5 by 16, the cube term also here. Okay, so okay, so we have done that. Now so we have many terms now, but you realize that here is the first order in r prime by r. Okay, but there is a square here. In this square, there will also be a contribution for first term in r prime by r. All right, and hence I must gather all the orders in terms of r prime by r. All right, so I just open them up and gather the terms and write it down. Okay, so you can do that in longhand also, but I have already done that. And then the first term is of course r prime cos alpha, this is power 1. In the second power there are two terms. Okay, 3 cos square alpha minus 1 minus 1 by 2, and so order, so r square and 3 terms, and there are higher terms also. Okay, but we would be interested in actually these 3 terms mostly, this also when required. All right, so this is straightforward itself. So let's remind what we did. We started with the potential, then we expressed 1 by curly r, okay, as a function of 1 by r, in which epsilon was small, expanded it, and got my expansion of 1 by r. So far I have not plugged this into my potential. This is just an expansion of 1 by r, curly r, in terms of 1 by r, which is the field point. Okay, this is the source to field point, and this is from my origin to, so I've gotten 1 by r in this series. Okay, so let's now plug that into my potential and get the sum of multiple moments. We'll do that. So I am rewriting that. Okay, you will write this enough that by the time you end this video, you would know them by heart. Okay, so again, I've just repeated from the last slide here. All right, so this I can write down. Okay, now this is might come to a surprise that this can be very compactly be written down as a sum of series. Okay, from n going to 0 to infinity, and a particular series which is very well known in physics, it, or in maths, it keeps popping up, this called Legendre series. You will learn it in your maths courses, and physics students will get in their harmonic oscillator problem, or when you are doing linear analysis, you would get to know spherical harmonics, Bessel's functions, and Legendre series very intimately. This is one of them. All right, we don't use them very much here, but at least it's a surprising that it keeps popping up in various, okay, and it can be so neatly be summarized that this, in fact, it can be taken to be a definition of this function itself. This is called Legendre series, okay. This is Legendre polynomial in the variable cos alpha, okay. So suppose cos alpha was x, then we know it, and this is Legendre. So P, if n is equal to 0, P naught x is equal to 1, and P1 x is equal to x, and so on and so forth. These exact terms come. Okay, surprising, but it does. All right. So these polynomials occur as solution of a very special differential equation, and that's why they keep popping up. But they can be generated also from this. Okay, that is Pnx. We are not going to use in this course. Okay, so nx derivative of x square minus 1n, and so these can be this is a generator of these functions. This can be defined as this. So for us, x is cos alpha is x. All right. So that's let's substitute this expansion into our v expression. Okay, that was our aim. So let's do that. So v of r was this. Okay, dq by r, and now we have gotten this expansion. So we'll plug this expansion in terms of 1 by r and r prime by r into the potential. Let's do that. So that is, I'm just plugging that in. Okay, writing. Uh, so I've taken 1 by r out. So there was already 1 by r out. So it 1 by r. So n is goes from 0 to infinity, and that's why it is n plus 1. And this in under integral is r prime to the power n. Okay, cos alpha rho prime. So now everything here is uh, r prime is the source distribution, rho prime is source distribution, this is differential element source distribution, except that this cos alpha is relates the source point to the field point, the angle between the r prime and r. So this r prime by r, one r has been taken out here. Okay, so that is why it becomes Rn plus 1, and there are infinite terms here. So now my expansion is complete. This integral is there, which has this cos alpha term in this. Okay, so but also note that I could take r out here because the integration is in prime coordinates, and that is why I could take this out. So as far as this integration is concerned, r is a constant. That is from the source to the field, from the origin to the field, wherever I've chosen the origin. Okay, r prime changes is being integrated under prime coordinates, but not on r. Okay, so I'll write down now. Okay, I'll expand it again, write it down. So 1 by 4 pi epsilon naught. The first term has 1 by r, and this is nothing but the charge distribution. 1 by r square, but in terms of the r prime cos alpha, and this is again the charge dq, rho r prime d2 d tau prime. 1 by r cube. Again, here also, it is cos alpha is the one, which is from source to the field point, 3 by 2 cos square alpha minus half, rho and forth. So at least I have three terms now, first term, second term, and third term. So rest of the two videos will worry about these three terms. Okay, so let's say what are these terms? This we call the monopole term, because this is nothing but, you can see it is just a summation or integral of, suppose there were only discrete charges, is be just a sum of that, or is a total charge. So that's why we call it the monopole. All right, so that is just the total, as if there was one charge that is integral of this. That's the monopole term. Then this is called the dipole term. Okay, this is the first moment, because there is a position getting averaged over the dq. Okay, so r prime cos alpha averaged over dq, and this goes in potential as 1 by r square. So this is the dipole term. You can guess what is the next. So dipole term, we know, we are familiar with this dumbbell model of the dipole, right? Okay, where there is a minus q and there is a plus q, and so this represents that. So this is a mnemonic, or is icon, should I say? Okay, so this is the icon for this particular term, the dipole term. Okay, so integral is the first moment with r prime cos alpha rho r prime dq. Let's look at the next called quadrupole. Okay, its VR goes as 1 by r cube, and this the factor is 3 by 2 cos square alpha minus half, and this is d cube. And so this is, for example, is this. Okay, I have this is octuple. Okay, so the iconic for octuple would be a cube with plus and minus charges. Let's say these are the minus charges. Green one answer the minus charges. Okay, and these are the plus charges, so 8 of them. Okay, so quadruple. So we will not worry about the octuple term, but I just wanted to tell you that this is obtained in terms of its hierarchy. Okay, so monopole with only one charge, minus and plus q, dipole. Then there are, as if there are two dipoles. Okay, one dipole like this, another dipole like this, and that can give you 1 by r cube, which is quadrupole, and this is octupole. So this is now our aim of expanding the potential as a sum of multiple moments is sort of done. All right, that was my major aim. Okay, so this is octuple. All right. I am also interested in parametrizing this source charge distribution. Okay, this is this, but I've gotten the expansion. But every term, okay, involves to write it down again. Every term now involves this distribution. Okay, so every term has cos alpha, so these field points and the source point are sort of through this cos alpha are mixed up. All right, so I need to parameterize my my charge distribution in terms that I can associate only with the charge distribution, not where I'm taking. Okay, at the moment, if I change my field point here, I have to do my integrations again from starting from the with rho prime df prime. Can I do something such that I know this charge distribution in these terms, so that any a new point, I don't have to again deal with this whole charge distribution. So that is what I mean by what is, so to say, parameterizing. All right. Okay. So let's do. So I say that we notice that in this expansion, the source coordinates and field coordinates are mixed up under the integral. Can we characterize each component, each term, okay, in terms of the source charge distribution alone, so that it says something about the source distribution independent of the coordinates of the field where I want to evaluate the potential? That's the aim, written down in black and white. All right. So this is my the zeroth term, okay, which is just the and we call this the monopole term is V naught 1 by 4 pi epsilon naught 1 by r, this monopole term. And for this term, it is straightforward because this total charge has nothing to do with my field point. I can always get it. And V naught is simply Q by, suppose this is total charge, then V naught is simply Q by 4 pi epsilon naught. So the first term, there is no problem. Okay, this is that just sum it up Q and write down the first term as V naught Q by 4 pi epsilon naught r, nothing to do with my far point. Okay, the second term though has this r prime cos alpha. Okay, so and that is mixing up, so let's do something about it. It's called a dipole. Okay, uh, so for this term we can express, okay, this is the common technique that we'll do. Okay, so r prime cos alpha I can write down as r hat dot r prime, so r prime, but the angle is cos alpha, so r prime cos alpha. Okay, and then we define dipole moment of the distribution as, okay, so a p arrow r prime. Now this only considers the source coordinates. There's no field coordinate here. So r prime rho r prime theta prime, this is the first moment. That's why it's called dipole moment. That is where the charge, that particular dq is located. Okay, so into its position, sum it over, it's a vector. Okay, so that is the definition of the dipole moment. Look at this, this is the defining, I'm defining it. Okay, so now I can plug this definition into my V1. Okay, and then V dipole simply becomes So nice. Okay. So now if I know P, at every point I simply have to take the dot product with R hat, and I have my potential. I don't have to integrate every time. That is what I meant by parameterizing, and that's done. So the first term is the total charge. The second term is the first moment, that is R prime, rho R prime d2 prime, or you could say rho prime dq. That is the uh, we will discuss a lot more about this. So dipole moment is a vector like any other vector. So if you have two dipole moments, then there is magnitude and there is direction, and we can add them, we can subtract them, or whatever we want to do if they're pointing in different directions. Okay, so they are like, so this is the quadruple term. I will also do the same thing, but I will postpone that for the moment because, okay, so that's another part. So it's quadruple. We'll be defining a quadruple moment, just like monopole moment, a dipole moment. We'll be defining a quadruple moment, which is actually a tensor or a, so this is a vector, the tensor of the rank 2. All right, but I will come back to that in a later video. So we characterize the source in terms of monopole strength Q, dipole moment P, okay, and quadruple moment Q tensor, which I'll take up in the next video, in the next lecture. All right. So let's do so this is the dipole moment. Okay. So let's look at the monopole and dipole terms a little bit. So do they depend on the choice of the origin? That's a question. That's okay, because everything is in terms of at the far point in terms of the choice of the origin. So does the expansion depend on the choice of my origin? That's the next question to ask. Monopole, of course, is just a scalar. Okay, so if the total Q net is non-zero, this is the strongest term in the expansion, and the monopole term is just a scalar. The net charge is independent of the origin, of course. All right. If this term is non-zero, it is the next leading term. Okay, this is 1 by r. Okay, we know that it is p cos alpha by r square. Okay, so then this will be the term, this will be weaker term. Okay, but this could be non-zero. If this is zero, then this is the leading order term. If this is non-zero, all right. So v dipole is, of course, we know this. All right. I just explained that. That will be the next term. Now for discrete charges, okay, we can write down this as simply Qi Ri prime. If they're all discrete charges, where they're located, I1 to n. Suppose there are n charges, and the dipole moment will simply constitute this sum. Okay, the Qi and its location Ri prime. All right. So claim I'll just leave it at the moment at the claim. Okay, if the net charge is zero, okay, we'll prove it. Then the dipole moment is independent of origin. Okay, if the net charge is zero, we cannot say the same thing if the net charge is not zero. All right. So this is an important exception that if the net charge, if monopole term is not there, then the dipole term is independent of the choice of the origin. All right. Uh, so uh, if I, for example, this R plus is R minus is minus Q, and minus Q to plus Q, this distance is D. Okay. So the dipole is now considered as QD. You know from your this dumbbell model of the from high school, this is the iconic dipole, minus plus Q with a D in between. All right. So if you have a physical dipole with plus Q and minus Q at R plus prime and R prime, then P is QR plus prime. So this is simply Q into D. All right. So let's okay. Let me take up an example. Okay. So this will end this with an example. Uh, 4.1 multiple expansion of various line charges. Okay, so I've taken a line charge which depends on line charges which depend on Z. Okay, so there are three different cases. Okay, This k is a constant, cos pi z by 2a, lambda is k sine pi z by 2a, and this is k pi z by a. This is a and this is 2a. This one is sine and one is cos. Okay. So what we have to, what we have been asked is to find the leading order term in the multiple expansion of the potential in each case. Okay. So is it, this is an insulating rod, okay, in which you have actually stuck these charges. Actually, this is trying to simulate what happens to a metal when a signal comes, okay, and does the charge distribution along the line. But since we are not doing, since we are doing electrostatics, we say that this take a rod and simply stick this one-dimensional charges onto this rod. All right. So just to remind you the terms, okay, this is my distribution, and this is my expansion, multiple expansion, and my first term is uh, the uh, the monopole term, okay, and the second term can be written if I define P rho prime r prime rho r prime as the dipole moment, then it is if I've chosen spherical coordinate, then P dot r will be simply P cos theta r square if my P is pointing in Z direction. I'll describe this more, but okay, and then so this is the monopole term, this is the dipole term, this is the quadrupole term. All right. So we know this independent of origin. So let's look at these three cases. All right. So I have written down again this. Okay. So in this case, what what I do is this is cos alpha. Okay, for a very far point from this point. So what I do is I notice that from the center point alone, there is a distribution here, but I ignore that because it's a far point. So I can take this cos alpha out of the integral, okay, and um and sort of cos theta, and then my integral simply again is r double prime rho r prime d okay. So that integral, so I have taken this far sighted here because this is only something a very straightforward charge distribution that is between minus a to a. I am here somewhere here, and hence I take from center to that angle as alpha for all the points here, okay, and hence I'm taking this cos alpha out of this integral, all right, and defining this integral, okay, as okay, so I again repeat my V0, V1, V2 here, okay, so that you have a reference point. So now this is I have taken out, okay, for far field approximation oriented along Z axis, I take my spherical coordinates. So this is K, and that is how it becomes cos alpha has become cos theta, all right, because the angle between this and this, I think this is the angle, theta, and this is my point where I want my potential, all right. Okay. Uh, so this integral now for what happens r prime, this is only in variation in z, and hence the integral limits are from minus a to a, and z to the power n, r prime is simply z prime to the power n, lambda z. So rho r prime d prime gets replaced by my one-dimensional dq. dq is lambda as a function of z prime here, okay, into dz. All right. So in this particular case, let's take the first case. Okay. That is k cos pi z by 2a. Okay. And figure out this integral and hence this potential, the first term. That is, what is this term? Okay. Um, or how many terms? So minus a to a. So let me plot this lambda z for you through my hand. Okay. So that is lambda z, and this is my lambda z, right? So this is uh, lambda z in this side, and this is my z. All right. So pi z by 2a from minus I to a goes like that. Okay. Notice that this is always positive. All right. So you can always see what is going to happen. All right. So uh, so V naught, okay, I'd say 1 by 4 pi epsilon naught 1 by r. So minus a to a, I simply plug in this into this, pi z and dza. All right. So and that is 1 by 4 pi epsilon naught 1 by r. This integral is straightforward from minus a to a. This 4a, this constant k comes out a pi 1. Okay, so that is simply ak 4ak by pi is the integral. Okay, simple integral. Okay, so v mono is 1 pi 4 pi epsilon naught q by r. That is the leading term. Okay, and you can see I expected this because everything was positive here. Okay, and everything will add up to a charge. There is no minus charge here. Okay, so there's distance is negative, but charge is always positive. All right, so this distribution gives you a monopole. That's the leading order term. Okay, so if that's the leading order term, I don't even expect other terms to exist here. Okay, so let me go to the next distribution. So here, instead of cos, I have made sine pi z by a. Okay, and pi z by a. This was 2a, this is pi z by a. Let's plot it over. How does it look like now? Okay, now there is a positive part. Okay, and in the negative part, this is the origin O. In the negative part is also the charge becomes negative. Okay, so you can see it is symmetric. The charge distribution is symmetric. Okay, so and it is positive in one half and negative one half, and you know what to expect. Okay, so this will, of course, the total monopole term would be zero, because if you sum it up it will be zero. So you would expect a dipole term, of course, because it's distributed in space. All right, so this is my lambda z. So I can write my v1 1 by 4 pi epsilon 1 by r square. This is the for n is equal to 1, so z prime lambda z prime dz prime. All right, so then I'll write down my p. Okay, my p is z prime lambda z prime in terms of the momenta. Okay, and this is also a simple integral. I've just integrated out k sine pi z a. Okay, from minus a to a. All right, so this is a sine pi z by a and the cos pi z by a with minus a to a, and that is just, if you plug this values of minus a and a, you get k2a squared by pi, and the leading order term then is the p is simply k2a squared by pi. This is p. Okay, by and cos theta. All right, so that is v1 r theta. That's a example of a leading order being dipole. All right, so I could write down this in terms of this. Okay, so obviously this is a dipole term. Now let's take the the, the third case. Okay, which is cos, this which was sine, this is k cos pi z by. So let's plot that. How does it look like? So now there is, even in the first half, there is a negative and then goes positive. Then in the lower half, it goes positive and then negative, right? So you can expect, of course, this term is going to be zero. It is so arranged, this curve to be zero, and this you can expect it to be a quadruple. All right, let's see that expectation. So I find out my V2. You can calculate that these two terms will be zero. So I'm directly going into calculate V2, because from symmetry itself I expect that. So in this case, this will be Z prime square and lambda Z prime dz prime. Okay, so it's square term. The second term is a quadruple term. So this again straightforward integral z prime square k cos pi a z prime dz prime. Okay, so that is minus k 4a square by pi square. Okay, these integrals are easy integrals. Check that my calculation is right. Okay, so v2 r theta is, I can write down as 1 by 4 pi epsilon naught this 1 by 2 r cube 3 cos square theta minus 1. You remember I had taken out this. Okay, so this term is there. So 3 by 2 cos square theta half term, I translate it here. Okay, so this half has gone out 1 by 2 here. R cube is there, 3 cos square theta. Cos square alpha becomes cos square theta alpha, and this integral is this integral here. So, and this is my quadruple term. So I've deliberately taken three cases in which, in this case, only the monopole term survives. This case. In this case, only the dipole term survives. And in this case, only the quadrupole term survives. It's not true that always only one of them survives. It's possible that in some distribution, all three survive. Okay. But of course, their effect on the potential is going to be smaller and smaller. Okay. That is always true. Okay, so I hope this gives you an idea of what is multiple expansion. This is a simple case, but a very illustrative one. Uh, there is another example. In fact, this example is I had given in the exam last time, and hence I will not solve it. I'm leaving it as a practice problem. I'll put this in the practice problem. I'll just explain the problem that there is a minus lambda a, and there's a plus lambda of radius b, and we have to find out the on the axis p. You can do this actually uh, directly without doing multiple expansion, and that was the whole intention of trying to show that the relation between trying to find out. And suppose my field point goes to q, that is angle is 30 degree. Okay, then how does this change? We could not do that earlier. Okay, how does the potential, the field or the potential here change if I my field point goes 30 degree off axis? All right. And I also wanted to give you doing this because this is how a typical problem in the subjective test reads. This was exactly for 6 marks, various parts. So please try and do that. I'll not solve it here. So let's do a quick summary of multiple potential expansion. That VR, we write down, okay. So I'll write this down enough number of times that you remember. So this is the monopole term 1 by r, the dipole term 1 by r square with r prime cos alpha, and the quadrupole term 1 by r cube with 3 by 2 cos square alpha minus half, and everywhere it is dq rho r prime d tau prime under the integral. We are trying, this is the distribution that we are trying to do momenta of. Okay, so and this is my it's good to have this diagram always in mind. What is r prime, curly r prime, what is alpha, and what is, I have repeated this in many of my slides in the last in this lecture. So remember what we are trying to do. Let me say it in words. Weighted average of various powers of the distribution with their coefficients depending on the orientation of the field, cos alpha. All right. So we are, what are we doing? We're doing a weighted average. Okay. So this is weighted with nothing. This is weighted with r prime. This is weighted with this is the way uh, coefficient. Right. Okay. So let's, so v naught. Okay, that's my monopole term, which is has only q. Then my dipole term. Okay, and this is my dipole term can be expressed as simply p dot r hat. Okay, my field point, and this is my quadruple term r square. This is a, sorry, this is here, there's an r square missing, right? So this is single, this is r square 3 by 2 cos square alpha minus half. This is the second momenta, this is my first momenta, this is my 0th moment. Okay, and so monopole, dipole, and quadruple term. So we will next consider the physical interpretation and uses of these above terms in determining potential and field in detail. Okay, so I'll stop share here. Okay, and stop the recording. So please go through this